Hi, I'm Matheus from FMG, and today I'll present you the paper ChessMix Spatial Context Data Augmentation for Remote Sensing Semantic Segmentation. So, semantic segmentation is the process of performing dense image labeling, which means we are classifying every pixel from an input image. In remote sensing, there are many applications that take advantage of this process, such as urban monitoring, agriculture and environmental management, and many others. The problem is that it is too difficult to obtain remote sensing images since they are usually very expensive or sometimes they do not present enough spatial resolution to work with. Furthermore, the label annotation process is also really costly for remote sensing semantic segmentation because we are usually dealing with high spatial resolution and sometimes we require specialists to perform the annotation. Because of that, only a few datasets are available for semantic segmentation, which makes us need to use data augmentation, which are methods that increase the trained sample size and diversity. For example, we have data warping methods such as geometric transformations and random erasing, and also oversampling methods such as GANs and image mixing. We noticed that there is a gap in the literature for methods made specifically for remote sensing semantic segmentation. Thus, we proposed ChessMix, which is a novel data augmentation method in this context. We try to bring the advantages of different data augmentation methods for ChessMix, such as the simplicity and versatility of geometric transformations, the robustness to overfitting of random erasing methods, and the capacity of generating new spatial relationships from oversampling methods. Here we have an example of a synthetic image created with ChessMix. So here in the left side we have an image that is composed by many patches taken across the whole dataset that are first transformed and then placed here in this chessboard-like pattern. This pattern was made in order to avoid spatial discontinuity between different patches. Here in the middle we have the corresponding ground truth, and during training these black spaces here are not backpropagated on the loss, so our network won't learn these patches that would have spatial discontinuity. And here on the right side we have the final input image that is pretty much the same as the first one. However, the difference is that we take those patches and we mirror them to the following black space, and we do this in order to avoid sending those black features across the network during the forward pass. So with this, the network won't see the black squares, and at the end it won't learn these positions because the corresponding ground truth does not backpropagate the loss on those black spaces. What the results will show later is that ChessMix is especially effective under the condition of low amount of training data, and is also really easy to employ. It's also one of the first, if not the first, work that studied the use of cut and mix techniques for semantic segmentation in remote sensing scenarios. It's also important to say that there are techniques other than data augmentation that can improve the quality of training, such as regularization, transfer learning, or the use of loss functions that are robust to class imbalance. However, we did not apply some of these in our work because we wanted to test specifically the ChessMix method. However, in practice, you can apply them along with ChessMix, so you can improve the results even further. So, for the proposed method, the first step is to divide the data from the whole data set in mini patches and pre-calculate their weights. This weight is supposed to say how probable that mini patch is of being chosen to make part of a new synthetic image. It is calculated as in this equation right here, where n is the number of classes from our problem. Cmax is the percentage of pixels from the class with more samples. So let's suppose that in this data set the building class is the most common one and it represents 40% of the data set. Then Cmax would be 40%. Ci is the percentage of pixels from the class I. So let's suppose we are looking at the car class and it represents 5% of the dataset. Then Ci for car would be 5%. And Pi is the number of pixels from the class I in the mini patch we are looking at. So basically what we are doing is giving a bigger weight to those mini patches that present the most number of pixels from the rarest class in our dataset. So after calculating these weights for all the mini patches, we will then start the process of creating new synthetic images. So first we will randomly select a mini patch based on that weight I showed before. We take this patch, we transform it using a set of predefined transformations that the user may desire. So let's suppose some flips, some rotations, and any other kind of transformation. We do the same thing with the label and place them in the corresponding place, the grid position of the new image being created. We then repeat this process for each one of the valid positions of our chessboard-like pattern in the new synthetic image. And then finally, we mirror these patches and place them in the following black space of the new synthetic image. And just remember, we keep those black spaces in the label because these spaces tell the network which parts should not be learned. But here we mirror in order to avoid black features across the network during the forward pass. So we perform this process for how many images you want to add to your training. So for the experimental setup, the semantic segmentation network we used was a pre-trained FCN ResNet 50, and we evaluated our method on 3 data sets. The first one is the Brazilian coffee scenes dataset. That is a binary dataset composed by pixels of class coffee or non-coffee, and 2 urban datasets, the Vingen dataset here and the Thetford dataset. This last one being the one with the least amount of pixels and the one where we got the best results. For more information about loss function, optimizer, hyperparameters, you can be referred to the paper, as there will be all the information you need. As for the ChessMix configuration, we extracted mini patches with 50% overlap, and we created 2 types of synthetic images using 2 different mini patch scale size. So we either have a 4x4 grid pattern when the scale is 1. So in this case, let's suppose the mini patch size is 100 by 100. And we have the cases where we have a 2x2 grid pattern for the next scale. So in this case, the mini patches would have, for example, 200 by 200. The final image, it's the same across each one of these scales. The only difference is in the mini patches inside of it, the size of the mini patches inside of it. As for transformations applied to the mini patches, we have chosen to use vertical flips, horizontal flips, random rotation by 90 degrees 0 or more times, transpose, grid distortion, and perspective transformation. So with the results, we wanted to answer 2 research questions. The first one being, can ChessMix improve the results when compared to data warping approaches? Data warping approaches are the most common data augmentation methods used in remote sensing semantic segmentation. So we wanted to see if ChessMix can be better than the usual approach. And 2, can ChessMix perform a better segmentation of the rarest objects? So as I said, our baseline will be data warping augmentation. Basically what we do then is for every image in our data set, before sending it to the network to the forward pass, we will apply a data warping augmentation in it. Our transformations were the same ones we used in the ChessMix approach, so it's the same list of transformations that I showed before, and we did this in order to make fair comparison between the baseline and our method. So the main difference between them is basically the chessboard-like pattern that ChessMix created. So here we have an example. So this original image can be applied vertical flips, random rotation, perspective transformation, so all those transformations that I listed before. We also trained the baseline network for the same amount of iterations as the network with ChessMix images, so then the baseline wouldn't be undertrained, so the comparison between the 2 of them will be fair. So here are the results in terms of normalized accuracy and intersection over union. And first of all, looking at the copy dataset here, we can see that both methods achieve pretty much the same value. For this case, it is understandable because this dataset only contains two classes, and there's a lot of intra-class variance, so it is difficult to perform segmentation on it, even using complex data augmentation methods. As for the urban datasets, we actually got better results with ChessMix, especially for the Thetford dataset, where we improved the intersection over union from 80 to 83, and the normalized accuracy from 86% to 94%, which is a very considerable value. Here we can see the results by each class individually. First of all, for the binding dataset, and here we can see that ChessMix managed to get a better accuracy for some of the classes, and for others it's staying pretty much the same. But the most important case here is the car class, where we managed to improve from 74% using the baseline to 76% using ChessMix. And this is an important result because this class is the one that is the most difficult one to segment. It's the rarest class in the data set, apart from the background class that is not listed here. This is actually a considerable improvement for such a difficult class. As for the Thetford dataset, here we got the best results. As I said, this dataset is the one with the least amount of available images. So the binding dataset was actually easier for the baseline because it already had enough images to train. But for Thetford, no, we don't have enough images here. So we need a better data augmentation method to help the training, and that's what ChessMix did. So here in this case, we can see a considerable improvement for at least 4 classes. For 3, we went from 91 in the baseline to 97% on ChessMix. Concrete roof went from 85 to 94. Vegetation went from 62 to 89. And bare soil went from 75 to almost 100% with the ChessMix method. Here we lost on the road class, which went from almost 100 to 88 using ChessMix images. However, this is a good trade-off. We managed to improve the other classes that are less present in the dataset a lot, and the normalized accuracy that I showed on the table 4 shows exactly this conclusion. So this is a great result for the ChessMix method under the most difficult condition, that is field labeled data. So in conclusion, ChessMix is a novel data augmentation strategy for remote sensing semantic segmentation datasets that tries to create new spatial relationships that may not be common or present in the original dataset. And ChessMix is a promising method. It showed that it can improve the performance when compared to the use of data warming techniques that are the most common ones, and it's especially effective for field labeled data, as the results for the Thetford dataset showed. For future works, we want to perform a deeper ablation study on our method and also experiment more refined techniques for the process of placing transformed mini patches in the synthetic images. So we want to consider the context of the pixels and maybe not even necessarily use the chessboard-like pattern. Here we have some information about the author and our laboratory, so feel free to visit our website to learn more about us. Thank you very much.